Ladies and gentlemen, honoured guests, it is my pleasure and privilege to welcome you this evening to these august halls of the Royal Automobile Club and to this memorial event for Professor Harold John Wootton.
I'm Ian Wootton, the eldest son of John Wootton, and it's my pleasure on behalf of the Wootton family to say a few words. So I would like to say that we're absolutely thrilled that this event has been put on and overwhelmed a little bit by all of the support that you've provided to us.
But John's interests were broad-ranging, and others will recall him for his ideas in other areas. 3 of these will be the focus of the lecture to follow, which is entitled Back to the Future. The lecture itself will comprise 3 presentations, each given by a once young person who worked with John on one of his ideas at the time, followed immediately with an update from one of today's young professionals to consider its relevance and effectiveness today.
So just to try and encapsulate what John was like, in 1980-something, there was a boot full of stuff in the car park at Cemetery Pales. It looked a bit like that, AI is generated. And John picked up his Motorola phone that looked like that, and he said, "One day, Andy, all of that will be in there." And I went, "Nah, that'll never happen, will it?" For those of you who use Waze, you could, for example, get navigated to a place called Cemetery Pales, which hopefully some of you will remember working in. And that takes me nicely on to the work about microscopic modelling that we were doing in what I'd like to think of as the skunk works of Wootton Jeffries. Those of you who are in the garage block, those luxurious porta cabins, and then having to go to the Garibaldi pub for lunch to be fueled to keep us going. But we were starting to understand how motorways ran and how to control it. And John and various other people in this room were filmed for Equinox in 1988 to explain how traffic worked.
Back on the M25, Equinox 3 is still making slow progress. They speed forward for short bursts and then come to a complete standstill for no apparent reason. These phantom traffic jams are a regular puzzle for drivers on the M25. They are, in fact, caused by shock waves. Speeding up the flow of traffic shows how they occur. When drivers bunch together, they rely on fast reactions. If one car brakes, the drivers behind tend to overreact and brake progressively harder till they come to a stop. From the original incident, a shock wave is triggered, which can be seen to pass slowly back up the stream of traffic, bringing it to a temporary halt. Flow in these conditions is highly unstable and seriously reduces the motorway's capacity. If we plot the speed and volume flow of traffic in a morning rush hour, it can be seen that once instability sets in, speed and volume flow are both greatly reduced. There's an opportunity here for technology to intervene.
Once a jam forms, it's actually very, very difficult to make it dissipate. And you have to try and find ways in controlling the traffic on a motorway to stop that initial incident affecting the traffic behind it.
So the question was, could we model each individual driver's interaction and overreaction? Well, the answer is yes, because it's now called micro-simulation, except we didn't call it that then. We call it car following, so what a driver does behind relative to the car in front. And we had this idea that it would be aggressive drivers who wanted to go right up them, and assertive drivers who didn't do that. So we developed this program called System, SISTM, which was developed for what was TRL, and then, as we've heard, John took that over and became TRL. And it was written in a language called Fortran, which I won't go into, but it ran on a 386 PC. Now, those of you who don't know how bad a 386 PC is, just imagine your worst ever mobile phone. It's probably 100 times faster than the computers we used. It could only simulate 100 vehicles at a time on a motorway, and it was all straight roads. So it looked a bit like a video game that was popular at the time called Frogger, where basically you had to get the frogs to cross the road and not be splattered by the cars. But it had the basic tools for modelling motorways and, more importantly, to learn how to control them. So what happened then was it was used for testing algorithms for what was called control motorways by TRG in Southampton, where John went on to lead, and some of you here today from. And that came up with the conclusion that if you're going to do speed control on motorways, you need red rings around it to mandate speed control. So I wonder whatever happened to that, eh? We assessed some ramp metering. We looked at the benefits of Midas. So Midas is a system that sets signals for queues. And then about 20 years ago, there was some work done by Southampton to look at designing what we now call ghost diverges. So where you're coming off the motorway and there's two lanes, those of you who are nerds will just see, oh, look, there's quite a good model there. There's quite a lot of work gone into that. But now, a micro sim, as we call it, is used as a tool globally. There are a couple of commercial suppliers, but there's also an open source system. So I'd like to thank PTV and Aimson for this eye candy of what they can do today in terms of not just motorways, but urban networks, pedestrians, trams, ports, etc., but also use it for control as well as modelling, which we'll hear about later. And I did a study with Atkins in 2017 about modelling automated vehicle benefits using this kind of technology. And for those of you who work for Wootton Jeffries, will know eventually it came into Atkins, so it's kind of full circle. We get some fabulous 3D fly-through animations rather than the 2D of Frogger. But it still needs really good input data, and maybe you can get that from cameras, and we'll come on to that in a bit. But it sometimes struggles for that motorway breakdown that you saw on that Checks Notes 37-year-old piece of video, because drivers are unpredictable. And one of the paradoxes is it's much easier to model autonomous vehicles because they're not unpredictable. So that's where we've got to, starting off with John. And what I'd like to do now is to pass over to Vittoria, who's going to talk from her company Mince Simulations about not so much where the past, but where we're going with microsim. So thank you.
Thank you, Andy. Hi, I'm Vittoria Parisi, Head of Product at Immense. Immense is a product company. We use traffic simulation techniques to model the days in the life of places and assess the real impact of roadworks, diversion routes, on complex scenarios quickly and efficiently. So all the methods that Andy has described, they have improved, they are maturing, but they're still data hungry. But with the advent of the connected vehicle data and traveler insights from mobile handsets, we've been able to develop new approaches and adopt these approaches. So basically at Immense, we've gone from an old approach where we have siloed planning and operations to a new approach where we have an integrated solution. So we embedded these traffic simulation techniques into everyday tools that traffic operators can use to manage and plan the network. So we provide simulation as a service. So in the past, what we've done was building models, base models that would take several months to be validated and calibrated. And then by the time we got insights from these models, they would be already outdated. On the operation side, we would always rely on operators' experience and knowledge rather than on an evidence base provided by models. So with the new methodologies and the approaches that we've been developed and the data that now we've available, we're able to build base models quite quickly and provide these models in weeks rather than in months. And we then can provide insights in minutes rather than in weeks. So we've also built some tools that are accessible to modelers and non-modelers in order to provide quick insights and make the right decisions in an informed and timely manner. We've deployed our methods in both on the operation side and on the planning side. A recent example, which is worth mentioning, is the work that we've been doing with TfL, Transport for London, and some others on representing the travelers' decisions on the network when it comes to rerouting. And this has enabled us to provide streamlined assessment of where congestion hotspots might happen and where temporary roadworks might be needed. So in this video here, you can see like vehicles moving around and there is like a road closure happening happening between 7 a.m. and 9 a.m. in that particular location. And you see that when the closure happens, then there are two types of drivers, green drivers and purple drivers. The green drivers are the ones that respond to congestion around the network. So they're all, they are aware of the situation around the network, and they are the sat-nav type of vehicles that reroute much earlier, while the purple ones are the conservative ones. So the ones that actually take the route from origin to destination and they just reroute at the last moment. So this is just one example of how microsimulation techniques and travel behavior is important in this type of decision making. On the planning side, here is an example of how we've used simulation techniques to plan urban services in an island in the Middle East. And we've combined together travel demand data, multimodal transport, fleet operations, and transport network to come up with the best efficient options for the island per se. So where is the strength of these methods? The strength is in asking, what if? What if we change something? What are the effects and how big they are? So it's about comparing the do nothing versus the do something versus the do something else. The way we can do that is by is if we have only like good enough base models that we can build consistently, cheaply, and quickly. But that's always is currently the challenge. And the opportunity is to provide understandable results to operational decision makers so they can make those decisions in a timely manner. And this, of course, is all possible thanks to the early work led by John Wootton.
And I want to talk to you about some research that I carried out, that whilst John wasn't actually involved in it directly, he was a key enabler, both of the research itself, but also of me as an individual and my career development, because subsequent to this, I actually joined the firm working with David as the project manager for Pleiades, of all things. And what I want to do quickly is just kind of show you that it's one thing to be able to handle and manipulate image data, but actually whether that's really vision is quite another thing. Let me take you back, to the 1980s. Remember that decade? Many of you do. CCTV was just really starting to be deployed, and we had a number of challenges. You've already seen one, which was this problem of phantom queues and queuing on motorways, but also things like turning movements at junctions were quite difficult to obtain, and often you were having to do quite difficult survey work. So CCTV was a great attraction because you've got a wide area view, you can see multiple lanes, you can watch traffic spatial behavior, and it's quite easy for us to understand. We can integrate with it. We know what it's about. So there's also the potential for actually reading more and more information. But you also have to remember, we were still in the analog universe. CCTV, 512 by 512 picture elements, pixels, but actually that was being foolish. It was actually 2 times 256 lines. Quarter of a megabyte of data for each image. So something like 6 megabytes of data per second. Andy mentioned 386 computers. You try and get a 386 computer to do 6.25 megabytes of data per second, you're going to hit some problems. So we were just starting to see solid state sensors for the cameras themselves, but everything else was analog. Output was all via copper cable. Recording was all on videotape. Remember the days of videotape. So the technology we had available created some opportunities. My then supervisor and the investigator of the initial research I carried out, Dr. Lewis Wilson, who's here today, he was actually in a building alongside the Department of Physics, and they built a thing called the CLIP-4 parallel processor. Now, at that time, there was a kind of feeling that individual processors themselves were kind of getting towards the limit, so what we needed was a lot of processors all working together. And they built this array of just over 9,000 processors aligned in a square matrix that could process each picture element individually and in parallel. It was about the size of a wardrobe, and you had to have something about the size of a chest of drawers to control it. But at this time, the good old PCs were just starting to turn up on the desktop. So we had 80386, 25 megahertz, 4 megabytes of RAM, plus we needed some additional kit to actually grab the frames from the videotape, and then some specialist video boards that can handle the data. But the difference between these two is that 96 by 96 pixels is not very dense, and it means that it's very, very difficult to pick out objects at any distance. And if you do some fairly basic geometry, you find out it's something between 50 and 90 meters. It's really not that useful, particularly when you're trying to look down a motorway. The IBM AT solution could actually look a lot further, but it was a lot slower. So we had to think around that. And just because we keep comparing things to mobile phones, in my pocket is this mobile phone. And basically you can see that everything that was a K or an M is now an M or a G. It has parallel processing. It can record 3 hours of high resolution video in my pocket with a battery that lasts for 24 hours. So things have moved on hugely. And to give it some kind of scale, this represents an exponential growth of doubling about every 3 to 4 years. So here's some actually the research outcomes we achieved. We did manage to track vehicles round a very limited junction. And you can see here we've got 3 different vehicles that we were able to identify using the CLIP parallel processor. But we could see that this was quite difficult. It was quite difficult to segment out individual vehicles as they enter the junction. With the IBM AT system, which we gave the acronym INCAPAX to, we actually developed a system that could see those phantom queues on the motorway, shown in red here. And we were actually able to get together and look at a lot of data. And Wootton Jeffries were instrumental in gathering this data for us. Andy Graham, Keith Keane, Dave Kelly all worked with me at John's behest to gather a whole range of different videotapes that we could use. One thing we did discover, though, was when you go out to record congestion, it disappears. So maybe we should do more recording. Oops. So the other thing we have to think about is it's not just about the sensor, it's about the system. And this is a very early system diagram from a project that was funded through the European Union. Again, this was John supporting collaboration, international collaboration. We had half a dozen companies involved with this from Spain, from Belgium, from France. We had several people promoting different computer vision image processing solutions. And we had a whole system that could take this disparate data and create an output that can be used by the traffic controllers. So we were actually really moving things forward. I think one of the more interesting things about this is it actually did get to be shown on Tomorrow's World. I didn't appear, but the system did, although I'm crouched behind a desk, desperately waiting for a cue to press the button at the right time. So, where have we got to today? Well, CCTV image processing is widely used. ANPR is now pretty well ubiquitous. It's everywhere. If you drove here today, even if you drove to the station, you will have had your number plate read multiple times. Queue detection is being done, but generally in things like tunnels. We are seeing individual vehicle control, not vehicle, junction control, and there is pedestrian and cycle detection. But these are all quite constrained things. They use specialist hardware. They've got rid of a lot of the externalities to do with lighting conditions. But we're now at this kind of developing stage where we're actually seeing some really interesting things, where we're actually able to start bringing in the context of vision that I think is actually going to be helpful in turning things that are great most of the time, but some of the time they actually fail to operate. And a lot of the time, they're not providing that certainty of outcome that we can use for control and for true operations. So I want to hand over now, but before I go, I just want to say that as I move on to fade off in my career, I have more time for reflection. And one of the things that I can reflect about is that I developed something that's been on the end of Maggie Philbin's finger. So now I'd like to invite Nicolette to come up and give us some really interesting stuff about what's happening today.
Good evening. Today we are here. So Dr. Hoos has taken us through the journey of computer vision, and I'm here to ask a simple question. How will that CCTV analytics transform road safety? So as we know, every day Thousands of hours are being recorded from our road network, but most of it, we don't really see it. So the current CCTV system is the eyes on our road network. It is trustworthy, it is operationally robust, and it comes with a lot of opportunities. And it's mostly there to support traffic and incident response. The infrastructure is mostly predominantly pan, tilt, zoom cameras, and they are designed primarily for operational monitoring. And the resolution of these cameras is aligned with the original requirements when they were implemented on the road network. And they also go through multiple analog to digital conversions, which can introduce latency. So how can we actually watch this video and understand the data from this video? Let me show you a few examples that we do at National Highways. Stopped vehicle detection is the most safety critical challenge on the motorway. What you are seeing here is automation supporting the operator in order to identify the vehicle, in order to get a quicker response time, because this can help save lives. Here you're seeing two different types of cameras where we can actually identify the stopped vehicles. So the automation is helping the operator. It is not replacing the human. It is actually giving back time where seconds are really important. Another example is this slide. So maybe it is more subtle, but arguably more powerful. This is because this is a near miss. It is not a collision. It is not incident reporting, but it does not even show in our data, unfortunately. So what we're doing here is we're using trajectories to identify whether the vehicles, if they continued on that same journey, a collision would have happened, which is represented by the time to collision in the bottom picture, which is 835 seconds, which is less than